Log on, tune in, find out. Another good idea from Cambridge.
Well, once again, a very warm welcome to this 26th series of Darwin College lectures. Our theme this year, as you know, is beauty, and this series has been conceived and organised by Lauren Arrington, Zoe Leinhardt, Philip David and Jessie Homan. And they've also, as an adjunct, arranged a beauty walk at the Fitzwilliam Museum, a sort of do-it-yourself aesthetic experience, and many thanks to the Fitzwilliam Museum for that. And while I'm on thanks, they couldn't be here tonight, but many thanks to Richard and Anne King, whose generosity enables us to run these lectures. The team who put this together, I think their choice of topics has been guided by the essentially paradoxical nature of beauty. So during the course of the next 8 weeks, we're going to be hearing about the grotesque and the sublime, about beauty at the level of the quantum and of the cosmos, how we perceive beauty and how it affects us, and beauty in the service of happiness and beauty in the service of terror. So it should be a really interesting range of talks. And we're starting with beauty in scientific thinking. And this subject, the title is Beauty and Truth. And as speaker, we're very honoured to have Professor Lord Robert May. He's currently at Oxford and Imperial College. He's held posts at Harvard, his native Sydney, and at Princeton. He is, as many of you will know, a scientist of quite remarkable breadth of achievement, and his modelling of unstable dynamic systems has been enormously influential across a range of subjects in theoretical ecology, in epidemiology and in biodiversity. And in this month's Nature, he, I think, wins prizes by having a paper on systemic risk in banking. Indeed, yesterday he even made the Financial Times, which for an engineer come physicist come zoologist is not bad going. Professor May's been President of the Royal Society, and he's been the Chief Scientific Advisor to Her Majesty's Government, a role which must have given him ample opportunity to reflect on the use and the misuse of truth. The title is Beauty and Truth, and it's a pleasure to introduce Professor May.
First, a piece of self-advertisement. The cover illustration of Nature has the facade of Lehman Brothers with a jagged line like a graph going down from top left to bottom right. And I commend it to you. I think it was the organizers' intent that I should talk about beauty and mathematics. And I am, to a degree, going to do this, but I have more generously interpreted it as beauty and understanding how the world works. Our attempts to understand how the world around us works, I believe, go back tens, hundreds of thousands of years before recorded history began. They're written in Stonehenge and the caves of Altamira and other places where it seems to me the most plausible interpretation of what you see is a mixture of artistic creativity but seamlessly blended with an attempt to understand and influence the otherwise bewildering world around. But I'm going to go further than that, actually, and impose upon the talk more of a structure that I find congenial. And I'm going to begin by talking not so much about beauty and truth, but about truth and beauty, and I'm going to distinguish several different kinds of truth. I'm going to begin, indeed, by talking about mathematics, about truths which are absolute, where you make certain assumptions and you prove things. And they may have relevance to the real world, but they are closed logical systems, often, I hope to convince you, with their own peculiar, if icy, beauty, but they're absolute truths. And they shade into our attempts to understand the world around us, where the truths we strive for are necessarily always contingent, because we're trying, whereas we can prove if two sides of a triangle are equal, the two angles are equal, we can't in the same sense prove the sun is going to rise tomorrow. It's an extremely good working hypothesis, but it doesn't have the same kind of truth. And I'm going to talk a little bit about that. And in short, the organization of this talk is going to run along a line where I'm going to talk about mathematics and beauty in a quite real sense, and then in a more, I'm going to talk a little bit about moving to the real world, natural sciences, and the role that elegance and beauty plays sometimes and has played in that quest, and then I'm going to round it up with some more general remarks. So to begin with the quest for mathematical truths, my first acquaintance with this, and it'd be similar to some of the older people in the audience, was Euclidean geometry. And I remember at the age of 12 being presented with one of those basic theorems, one of the first propositions in Euclid. If two sides of a triangle are equal, then the two angles are equal. And I remember actually at the age of 12 having an argument with the teacher in which I said, in effect, this is obvious by symmetry, for God's sake, why fuss around? And I was rightly admonished for this, because what Euclid did was drop a perpendicular to the base, and then two triangles are congruent if either all three sides are the same, or two angles are the same, two sides are the same, and the included angle, or if it's one of them's a right angle, any angle is the same, or if one side is the same and the angles at either side. So Euclid simply said, in the triangle ABD and the triangle ACD, AB equals AC, that you were given, and AD equals AD, they're common, and this is a right angle, therefore the angles are equal. And in the early 60s, when people were first beginning to build complicated, sophisticated computers, and when artificial intelligence was in its infancy, one of the things that somebody thought to do was say, let's build a computer to go through and see how good they are at proving Euclid's theorems. And let's begin with this one, because the computer's going to have to do something clever. It's going to have to drop a perpendicular. Let's see if it's up to it. And what did the computer do? The computer said, consider the triangle ABC and the triangle ACB. AB equals AC, AC equals AB, BC is common, therefore they're congruent, therefore the angles are equal, which is a rigorous version of what I had done at 12. Now, as mathematics developed pre-Newton, various things, just in purely numerical things, that we tend to often not even think about. The invention of the concept of zero, which belongs to the Arab, what we might now sometimes call the Islamic world, is a non-trivial discovery. And in fact, if you look at the way lifts, or as they call them, elevators, work in North America, the concept of zero hasn't made it that far, because they don't understand that the ground floor is the 0th floor. It's called the first floor simply because of a genuine lack of sophistication in the earlier days of the colony that hadn't really deserved. But I digress. Then came negative numbers, and that's a more sophisticated concept. But I'm now going to talk for a little bit about something that I find particularly engaging and which will lead us in some amusing directions: complex numbers. And so back to school, simple equation with one variable, think of a number, square it, multiply it by 2 and add 2, that's 0. So what's the number? Well, you can easily fiddle around with that. You can say x squared plus 2x plus 1 is just x plus 1 squared, and that's got to be equal to minus 1. Therefore, x is minus 1 plus or minus the square root of minus 1. The square root of minus 1, you may say? What the hell's that? That's a nonsense. That's not a nonsense. Let's define it to be a number or an entity. Let's call it I, the square root of minus 1. And now x will be minus 1 plus or minus the square root of I, plus or minus I. And we can think of the solution plane for solutions of equations with one variable, where the solutions may be real numbers or they may be complex numbers. We may think of them as being in some sort of two-dimensional plane in which the horizontal axis is real bits and the vertical axis is imaginary bits, and in that space a complex number z will have a real bit and an imaginary bit. Well, why would we do this? One of the things, and I'm not going to lead you all the way through this, I just give you this, which I think is as beautiful an object in an intellectual sense as you're ever likely to find. If I took another 10 minutes to go through it, I could take you all the way there, but I'm just going to announce it. And I'm sure about half the people in the audience will be familiar with this formula, but it's a thing that really has genuine magic in it. It says, you take the base of natural logarithms, this transcendental number e, which is 2.7 and a bit, which is a number you get by solving the equation, how does something behave if the rate at which it's changing over time is exactly proportional to the magnitude of the object. If the change in x is equal to x, second after second after second, it will increase exponentially. X after time t will be this funny number e raised to the power t. So this is just a natural number. Be the same everywhere in the universe. You raise it to the power, this nonsense object, I, the square root of minus 1, semi-meaningless, multiply it by the ratio of a circle's circumference to its diameter, and blow me down, you get minus 1. That's a magical thing. Two fundamental constants and this nonsense number. And it's really useful, and it paves the way for what I'm going to do next. But I just mentioned in passing, not everybody finds this magic. There are people who just find it inconvenient, for example, that pi is not something it's just some complicated number. And one of the more amusing expressions of that is about 50 years ago, the Wisconsin legislature actually passed a bill that said pi we will define in Wisconsin as 3.2 for the convenience of the building industry. And the thing I find particularly amusing and amazing about that is, if you're going to redefine pi, why make it 3.2? Why not 3? It never got into being passed because the governor vetoed it. I'm now going to take a step back, and I'm going to talk about some more recent things that we've learned, and which will take us eventually in this quest for beauty into the complex plane. This more recent quest was foreshadowed about 100 years ago when, I've forgotten the name of the king, encroaching senility, but one of the Scandinavian kings offered a prize, it's in the late 1800s, to prove that the solar system as a whole was a closed system. And in the quest for this, Poincaré showed that if you started off simply with a three-body problem, like the Earth, Sun, and the Moon, it did really weird things that really rather precluded any crisp solution to this problem. I'm going to give you a simpler version of what we now call chaos. And again, many of you will be familiar with this. Here's a simple piece of mathematics. I stumbled across it in most of the earlier work, a century ago, was too hard to pursue before the advent of computers because it dealt with continuous systems and differential calculus, and you needed, in that case, at least three-dimensional systems before you could get the phenomenon I'm going to talk about. But if you deal with discrete systems where things change in discrete intervals, a number of knapweed gall flies in Whiteham Wood this year, next year, the year after, and you assume that the number next year, x of next year, is the number this year, x, times some intrinsic multiplicative constant times some negative feedback term that says that the intrinsic capacity to reproduce is diminished as the population becomes more abundant compared, and let's define, arbitrarily rescale it to 1 minus x. The relation then between the population this year, x of t, and the population next year, x of t plus 1, will be that solid parabolic curve. And you can then ask, you can then see from that that if the population is below this value here, lying along here, that is to say, it is below the point where the line of unchanging population intersects this equation that tells you the relation between generations. If the population's below that, it will tend to increase from year to year. And on the other hand, if it's above that point, it'll decrease from year to year. And you can then ask, how will all this depend on the value of this intrinsic growth rate? Well, you can easily see that if A is less than 1, the population is just going to decline to 0. But earlier intuition was that if the population value is bigger than 1, then it will settle one way or another to this equilibrium point. It's not as simple as that. If A is bigger than 1 but not too big, you get the population indeed settling to a nice, happy equilibrium. Displaced by environmental fluctuations, it'll come back. But beyond that, you begin to move into a more complicated regime where it goes stably up and down, driven by its own dynamics into going up and down. And then if you make it a bit bigger, it starts doing things that for all the world look like it's just random noise. Another way of looking at it is to say, what are the points on this equation where the system will either be steady or will return to, where are points which, if you put them exactly on the point with no forward or backward perturbation, it'd sit there. What are they? Well, at first there's just one stable point, and then this bifurcates to give you 2 such points, and the system oscillates between them, bifurcates again 4 times, and it comes on to this point where it just gets too messy really to understand. There are bits you can see what's happening. In this little window here, there's a cycle 3 where it goes from A to B to C, back to A to B to C, back to A to B to C. And this particular thing, in that simplest thing that a child could iterate on a hand calculator, once you get up to A around, if A is bigger than 4, the whole thing goes extinct, because going back to this diagram, you get out here, and so you've just gone back to 0. So we're looking at values of A between 1 and 4. As you go to A equals 4, it can jiggle around among any one of an infinite number of points along here. The work on, we call this chaos now because it's such a mess. the work that was done on differential equations needs at least 3 dimensions, and it's much harder to get intuitive understanding. 2 or 3 different mathematicians had found this earlier, the first publishing it in Finnish in the Finnish Journal of Physics, without having a sense of this was anything other than some elegant mathematical thingy. I had stumbled upon this bit of it, and I gave a seminar in Maryland and said, I don't know what happens next beyond here. And Jim York, who had understood what was happening here, but never realized it had come from this sort of cascade of period doublings, said, I know. And he had just published a paper that gave us the name chaos. Period 3 implies chaos, it's called. We both discovered then that other mathematicians had sort of known this, but they'd never thought it was particularly interesting. And Jim York is very fond of saying, we weren't the first to find this, but we were the last. Of course, we made a noise about how interesting it was. And its real interest is, not only do these things in a circuit, you've got this simple deterministic rule with one parameter, nothing unknown, but it's so sensitive to the initial conditions that you can't make long-term predictions. So here in the solid line, I start with the first x is 0.3. The dotted line, I make a mistake of about 1 part in 300. And before I've gone about half a dozen or more iterates out, the paths are entirely different. And that's much more than a piece of beautiful mathematics. That actually is the end of the Newtonian dream. Here is a system where we know everything about it. We can make, it opens a new window on short-term predictions, which one of my students parlayed into running Deutsche Securities USA for 4 or 5 years as a way. You can take what von Neumann and Ulam used as their random number generator for the first computer in MANIAC in 48 and test it with conventional tests for random numbers, and it says it's random numbers. It's actually, what they used was something we would today call a version of this quadratic map, and George Sugihara and I found a method using this of saying, well, we can at least tell you the next few so-called random numbers, although not further down the road. So although a conventional test would say von Neumann and Lamb were getting random numbers, we could tell you the next few, and George parlayed that into running investment things, which is how I got involved in the investment stuff in the first place. But I digress again. Let's, however, go on beyond that to let's go into 2 dimensions with that simple equation, but let's do it by the trick of just saying, let's put the variable in that simple little equation a complex variable. And in effect, of course, that makes that one-dimensional system. The next z is a constant times z times 1 minus z. 2 equations, one for the real part and one for the imaginary part. So it tells us the next x is this mixture of x and y, and the next y is this mixture of x and y. And they're a bit more complicated, but we can ask, and more commonly you see that equation written that way, which is equivalent. I skip past that. What that does, and I'm now going to show you some, and there will be others in the beauty exhibit later. From this, you can generate patterns as complex and as bizarre as you can imagine, and more. They're called Julius sets in general, from a mathematician who first noted them 100 years ago almost, but they're more familiarly associated with the name of Benoit Mandelbrot, who again rediscovered them, but saw how interesting they were. And I'm going to show you what I mean by that in the case of one particular member of this class that's called the Mandelbrot set. Here it is in its simplest form, and how this has been obtained. There's really an x-axis along here and an imaginary axis somewhere up here. But how it's been done essentially, he's taken that simple complex plane two-dimensional version of the simple quadratic map, trivial equation, and looked for all the points in the complex plane which correspond to points where the next z equals z intersects the real z. So they might have, you mightn't come back there for many iterates, but they're points, they're the generalization. This is the two-dimensional generalization of that bifurcation diagram I showed a moment ago. And if you don't understand that, don't worry about it, you don't have to. Let me just describe how weird this thing is. This thing, the area it encloses, and you can't see all the details of the funny little bits on this figure, which is just to give an idea of it. The complicated details go out further. And I'll come back to that in a moment. But in broad outline, this encompasses a finite area. It's all enclosed by a circle of radius 2.5 centered on the origin in the complex plane. So its area is finite. Its boundary is infinite. Its boundary is, in principle, a line. A line is one-dimensional, except this line isn't one-dimensional. This line is two-dimensional. The more you look at it, the more detail you see. So this gives some idea of it, but you pick a little bit of it. You pick one of these bits here that's curling out, and you zoom in on it, and you look at it in more detail, and you see more detail. You look at one of these funny little things coming off here in more detail, and you see more detail. You can see them as a lot of elephants wandering along or whatever you like. And you can pick out a little bit of the detail there, and you'll see more detail. Astonishing, really astonishing set of things. The notion of going back to really sort of puts Euclid in perspective. Not only did he drop an unnecessary perpendicular, but all of Euclidean geometry is a special case which arguably is not very relevant to many objects in the real world, like coastlines, or maybe like the surface of a tree, as seen by small enough insects. One of the more amusing manifestations, this is crop circles generated by the Mandelbrot set out overnight by some group of pranksters down near Avebury. And there are, if I am to believe what I am told, a set of people who genuinely believe that this is a manifestation from outer space. Now I'm going to move on to beauty and the natural sciences, but before I do so, I want to emphasize not all mathematical proofs are beautiful. A classic mathematical quest has been to prove the so-called four-color theorem. It's a theorem that says any map, any two-dimensional map on a surface, with any arbitrary arrangements of territorial borders among countries or cantons or whatever you want to distinguish, can be meaningfully and unambiguously, clearly colored with only four colors. That's a problem's been around for a long time. Finally, as computers became more sophisticated, it's been proved because you can examine it and see, set aside what I believe, and I hope I'm right in the number here, something like several hundred exceptional cases that one proof doesn't cover, and then you can explore each of these on a computer and show that each one of them, very tediously, can also be done. And the question is, if you're a pure mathematician, have you proved the theorem? You've proved the theorem's right, but I mean, it's so ugly. And furthermore, why do you want to prove theorems? You usually want to prove theorems to understand things better. And if you really understood things better, if you got a list of exceptional cases and then tediously went through all of them, well, different people will have different views, and I'm sure the people who proved the theorem have a different view from the one that I perhaps just expressed. So I thought, again, I feel it's one of these things that I'm content to say, well, it's obvious anyway. And there are quite a few things like that. And I mean, another one recently, and many of you in the audience may be unaware, is the game of drafts with best play on both sides a win for the first player, the second player, or as a draw. The draft's a simple game. It's only very recently that a huge number crunching exercise has shown drafts, best play both sides as a draw. Chess is vastly more complicated, and I find it hard to imagine that there'll ever be an answer to the question, is chess win for white, win for black, or a draw with best play on both sides? I find it hard to believe that'll ever be answered. But even if it was, I don't think it would be interesting, the way it'd have to be answered. It'd be a pity, it'd make a shambles of the game. But... Okay, beauty and natural sciences. Then again, we've got to remind ourselves the quest to understand the world around us goes back well before recorded history. It's written there in caves of Lascaux and elsewhere. And its beginnings were pretty practical, not very theoretical. They begin more or less in the Fertile Crescent, they begin in Babylon, and they've bequeathed to us the number 60. It was very pragmatic, trying to construct calendars and do stuff with a counting system based on 60. And although they haven't left much else in the world of science, they've left that basic counting thing, which is still the way we measure angles and so on. The Greeks were different. The Greeks had a notion that beauty was a guide somehow. And that was both a nice idea and a helpful idea, and at the same time a slightly misleading one. The conventional view of Ptolemy and Copernicus, the thing in simplified texts, is that when you actually started looking in detail at the motion of the planets and us around the sun, it didn't actually fit circles. So people had to fudge it by doing all this stuff with epicycles. And then along came Copernicus, and the sun was at the middle, and everything was okay. Well, it's not like that at all. The main thing Copernicus did, Ptolemy's construction of the Earth going around the sun, for example, with an epicycle, is in fact, it takes the Greek fixation on the perfection of the circle, because the heavens have got to be all circle, but it gives you, to second order in the eccentricity of the ellipse we now know it is, it gives you a correct description. And what Copernicus did, make a big thing that he put the sun at the center, but he didn't put the sun at the center. He put the sun not at the center and the Earth going around it, he put the sun off-center. In off-center of a circle, in a construction which also was to exactly the same approximation as Ptolemy's epicycles, correct to second order in the eccentricity of the ellipse. The big fuss about which is at the center is sort of silly, and indeed the thing that tests people's knowledge of science, does the Earth go around the sun around the Earth? The right answer is both. It's a silly question. But if you want to get the right answer on the GREs, you better say the Earth goes around the sun. That fixation, in short, on circles wasn't necessarily helpful because you could argue it hindered what Kepler noticed empirically when he got really into the data, that it was an ellipse, in effect, by sweeping out equal areas and equal times. And that paved the way for Newton. Perhaps the clearest articulation of the notion of a quest for beauty as a guide is Galileo. And this comes, interestingly, at the same time as people are beginning to shift the focus from thinking you decide how the world works by thinking about it, appealing to old authorities, and being guided by abstractions like it must be beautiful. So if you want to decide do heavy bodies fall faster than not so heavy bodies, you appeal to the authorities. You don't actually think of taking a heavy body and a light body and walking to the top of the Tower of Pisa and dropping him or something. Appeal to authorities. It's basically, up to that point, the natural sciences were pretty much in the same state that economics still is. Interestingly, what we realize today is that while there may have been a basically sound point in what Galileo said, Galileo's sense that it was mathematics doing it, and therefore it was triangles, circles, and geometric objects, that bit was wrong. It's not always cycles. It's not always in the phase plane nice things. It's not always smooth cycles. It's very often chaos and fractals and strange attractors. That's a more complicated world, but it still has strong elements, with mathematics being, in the words of Jean Vigna, unusually effective in describing the world. Now, at this point, it would be easy to sort of go off and say, essentially, beauty is truth and truth is beauty, and that's why, of course, I picked the topic. However, to complete it by saying that's all you know and all you need to know is really not really true. Because the crucial thing that Galileo was also associated with was the invention of the experimental method. You don't appeal to authorities, you go and do experiments. Then, of course, it was foreshadowed by other people. One of my favorites is Bishop Grosseteste. One of the things that Aristotle bequeathed to us, oddly enough, and was made canonical by Aquinas, was that, believe it or not, badgers have the legs on the right side, or maybe it's the left side, shorter than on the other side, because they always go up hills from right to left, or left to right. I forget which. Wonderful piece of beautiful theory. Bishop Grosseteste was sufficiently bold to question this canonical utterance, just as well the present pontiff wasn't around at the time, and he actually looked at badgers and found they didn't. So I mean, it was beginning, but it really is only the last few hundred years that we've come to the full embrace of the fact that an ugly fact trumps a beautiful theory. And that is what has set in chain the still accelerating understanding of the world, which we've used unremittingly with good intentions, make people healthier, live longer lives, more energy subsidies, and are now having to deal with the unintended consequences. But even in that, beauty is still entrained. And let me move toward the end with two more examples. And special relativity is a beautiful such example. And again, I'm going to do this in a rather superficial way, but just to give a feel for it. Toward the end of the 1800s, the accepted understanding of electricity and magnetism and a lot of other things was that there was some curious ether that propagated the fields that you saw, as it were, and people set out to try and measure to what extent we were moving relevant to this background by looking at things, and the experiment seemed unambiguously to point to the fact that it didn't matter which way you looked or how fast you moved or how slow you moved, the speed of light was absolutely invariant. Didn't matter whether you were running toward the photons or away from the photons, the speed of light was the same everywhere. Which is entirely inconsistent with the feeling that if anything's absolute, it's notions of space and time. You know, 10 minutes is 10 minutes. 1 yard is 1 yard. Doesn't matter whether it's going fast or slow. But Einstein's great observation was that if indeed the speed of light is an absolute constant, and it is true also that the laws of physics are the same at all places and all times, And there are theories around today that say maybe if you mean really long times, maybe not. But just stick with this. Laws of physics are the same all places and all times. Speed of light's a constant. That means notions of time and length, and thus velocity and momentum, have to be modified. And Einstein set out to find a consistent framework treating the four variables of the three dimensions of space and the dimension of time in a symmetrical way, and pursued that to its logical conclusion, which was that the measure of momentum of an object, for example, its mass times its velocity, has to be modified by the inverse square root of 1 minus the ratio of that velocity to the velocity of light squared. And in order to bring in the symmetry of putting space and time together, you're forced to the conclusion that accompanying the three dimensions of momentum, velocity in three-dimensional space, comes energy, and you're going to assign, in a way that might have seemed peculiar, a rest energy of objects that you don't physically measure so much as mc squared, in the sense that if something happens to the object in such a way that it does lose mass, as happens in nuclear fission, then that energy which is conserved must appear somewhere else. But it does have that rest energy. And at first this seemed maybe nonsense, or it's certainly an abstraction. Nobody asked him, as the, I think it was the Prime Minister who asked Faraday, what's the use of what you're doing? And Faraday said, I don't know, but I'm sure you will learn to tax it. Which was just as true then, less true then than today. In short, in this canonical format of treating the thing symmetrically, you have to redefine energy in a curious way that ends up giving you the energy is mc squared over the 1 minus v over c all squared, square rooted. And then ordinarily, in any usual experience, the velocity we're dealing with is vastly less than the velocity of light. So this comes back to give you half mv squared, which is what you learned in secondary school, if not primary school. But extending this, and that is an example of something that turned out to be extraordinarily consequential. It's not so much that people learned to tax the discovery as they learned to build weapons of mass destruction from it. Continuing the quest, the person that many people, including myself, would rank right there with Einstein, but a less publicity-rich, and in some sense you could say that Einstein was not averse to publicity, whereas Dirac certainly was. I would rate him fully Einstein's equal. This is his memorial stone in Westminster Abbey, and it commemorates his extraordinary equation, which is written in deliberately simplified terms there. I'll write it again here. It's an equation that seeks to take the basic equation of quantum mechanics, the Schrödinger equation, and turn it into something that is relativistically sympathetic and handles the three variables of space and the variable of time together. So the Greek letter psi, the thing like a U with a vertical line through it, is the wave function that describes the state in space and time of the system you're talking about. The delta thingy there means derivatives with respect to three space dimensions of time dimension. I is our old friend, the square root of -1. What's it doing there? And gamma is a set of 4x4 matrices that have some kind of correspondence to the particles you're talking about. And the bizarre thing about this is, which at the time was really disconcerting, and I think is one of the most magical things in all of physics, if there's sense in what was done here, of the four particles you're talking about, started talking about electrons, two of them are electrons with either spins up or spins down. What are the other two? Dirac hoped they would turn out to be protons, the things that are much heavier than electrons, but really ought to be thought of as that time as their cousins or siblings, and that maybe someone had screwed up on measuring their mass, or there was some way of redefining it. It turns out, of course, the alternative was to assume there is a background sea of particles that we never see that are anti-electrons, that are like electrons except they've got positive charge. This seems beyond the wildest shores of madness. And so it did until they were found. Now, there are examples, in short, where our pursuit of truth has been guided by appeal to elegance and beauty in ways that I know I wouldn't have believed if you'd explained it to me as an abstract concept. I'm quite sure if when Dirac had written that equation down, rather than conjecture whether the things were protons or some background sea of negative particles, I would have said there's something wrong with the derivation. Quite convinced of that. I could have gone on, and I'm not going to. I had conjectured telling you some other things, but I figured you've probably had enough of this by this time. But there are also some really beautiful things you can do in both the life sciences and the physical sciences without knowing very much about the system, just asking what are the scaling laws. You know, there are three quantities, basic quantities things have. They have mass, they have length, and there's time enters. If you just write down those scaling laws, it is amazing the things you can show. A very simple one in biology that was done by somebody 300 years ago, and it's the cover of the wonderful book John Maynard Smith wrote on models in biology. It's a very simple scaling law argument that asks for organisms of different sizes that have ways of jumping up, whether they're horses or whether they're fleas, thinking about how they do it, what's the potential energy involved, what's the springiness involved. There's a dimensional argument that says, in fact, it's going to be independent of the size of the organism. And you can make a rough estimate. All organisms, if they're fit, ought to be able to jump about a metre, elevate their centre of gravity about a metre. That's what we do. It's what horses do. It's what fleas do. There are things that will jump higher and lower because evolution has forged them to be particularly jumpy or not very jumpy. It's a wonderful thing. And the really elegant thing about it, the cover illustration of John Maynard Smith's little book on models in biology has a little representational mouse. I should have had it on a slide, but I couldn't find the book in time. And it's, it's a square little mouse with springy legs. It was very distressful for John, who was what I sometimes did unkindly think of as an Etonian Marxist, that he was definitely he had Marxist sympathies, and it was a matter of real distress to him when his book was translated into Russian, and on the cover, completely changed, was a socialist realist mouse. More consequential, and again, a great story. It brought great joy to many people. When the first atom bomb test was conducted at Almagodro, one of the chief fluid dynamicists involved in that was a chap called G.I. Taylor, a Cambridge person that many of you will remember. And as it was going, he was sort of scribbling, nobody really noticed. And what he was taking note of was, as the mushroom cloud expanded, how was it expanding? What was he was measuring, getting an idea of what was its radius at a given time and keeping track of the time. He had thought before anything was done, what's going to go on here is there's going to be a lot of energy released when the fission effect occurs, and that energy is going to drive this cloud out, and it's going to have to go out against the density of air. So the two variables involved are the energy, mass, length squared, t time to the minus 2, and the density of the air, mass, divided by length cubed. You can cancel out the masses and you'll get a prediction that the radius is going to expand, radius to the fifth is going to go like t squared. So you're going to plot the logarithm of the radius against the logarithm of the time, you're going to get something of slope 0.4. And where it intercepts the axis will tell you the energy released. And he thought this was pretty nice, so he wrote a little 2-page paper. He sent it off to the Journal of Fluid Mechanics. They duly published it. And the General Groves and the people in the Manhattan Project went absolutely apeshit, because this was classified at the highest level. I really love it. I mean, in its own way, it's better than the jokes Feynman played on this bunch of people. And incidentally, it's the received wisdom, as I understand it, certainly in the circles in which I move, that the tight security Groves imposed on the Manhattan Project, and nobody talking to anybody else and stuff, actually retarded it. It didn't go faster by virtue of it all, it went slower, but that's another point. And my last example of these things, a very simple one, particularly for people who sail, which don't include me. I could, again, 5 minutes or so, I could give you a very, very simple dimensional argument that would tell you the bow waves that come away from ships, whether they're an oil tanker or whether they're a rowing boat, are coming out at an angle of about 23 degrees. It's an angle whose tangent is 1/2 root 2. And that comes from, again, there are all sorts of elegant things you can do. And my own prejudice is the nicest things in science, the things you can really trust, often these days are things where you have to have a huge computational exercise where you put in all the details, because there are going to be people who are going to want to see that. But I'm never going to trust that if it's not backed by something that stripped the thing to its essentials and can show me more or less on the back of an envelope what's going on. And I just venture for an instant into financial things, although I shouldn't. If I were supreme dictator of the universe, the first thing I would do for banking regulations would forbid the trading in instruments, which are alleged to be very clever. They're not. They're very computationally elaborate. Some of these things, if you wrote them as a prospectus, would be the equivalent of about 1 million pages. I'm quoting the Bank of England on that. I would forbid the trading in something like that on the grounds that the people who are doing it don't know what they're doing, and you shouldn't be allowed to do what you don't know what you're doing when it has such implications. So in some sense, I don't want to have left the... I want to have said something that I'm not quite sure how I want to say it, which is beauty is there everywhere in mathematics, almost everywhere in mathematics. In the sciences, it can often be quite magically important, and I've given you some examples. More commonly, it's things then build on that and their elaboration of it, and they're important by virtue of it, and they may seem more humdrum. But they are based on things, if they're really good, where you've really understood it. And I want to conclude by saying just a word of genuflecting in the direction of an alternative way of understanding the world around us, which has been with us again for at least 100,000 years, which is just how it all began. Beliefs, values. And I'm not wanting to put it down, but I'm just saying many of the things that bind society together have some of the characteristics of values that we need to all adhere to. And they're outside the framework I've been trying to talk about. So they're not necessarily bad. They're only bad when they take the form of trespassing into a domain where science has come and told you an answer. It hasn't told you an answer about how to conduct yourself personally, but but it has told you the answer to a conundrum. So if you want to know how the diversity of the world around us occurred, evolution tells you that now. And you're entitled, if you wish, I have every respect for it, some respect for it, to believe that the machinery was set in place by something divine. I think that's an unnecessary assumption, but if you wish to, it does no harm. On the other hand, it does do harm if you start teaching kids that the world was created in the year 4004. And there are many things like that, and it's not at all clear that at a time of particular difficulty in the history of this planet, the abdication of the attempt to really understand things in favor of embracing some set of answers, which very often is built around assumptions that women's status should be lower than men's, is unhelpful to us. I mean, we live in a time we tend to focus on one problem at a time. At the moment, we tend to focus on climate change. If you go back 30 years, we focused on population growth. If you look ahead 10 years, it would be my prediction we'll be focusing on food supplies. In 20 years, we'll be focusing on fresh water globally. That they're all part of the same thing. And what we really need is a coming together from people who hold beliefs about how the world ultimately happened, but don't let it trump detailed understanding of particular aspects that we need to come together to address. And it's not altogether clear to me that this belonged in a talk on truth and beauty, but it's certainly a part of truth, if not of beauty.
Well, there will be many people in this hall who have to struggle in their daily lives with thoughts about research assessment exercises and research excellence frameworks and impacts and all those things. So I hope you've all taken notes and that you know that the real importance is of being last to discover something. Those who assess impact will have to take that into account. Professor May's given us a lovely account of as he described it, the quest for beauty as a guide to understanding nature. He's taken us from Euclid to Dirac. But I think it was the philosopher Alfred North Whitehead who said, seek simplicity and mistrust it. And the other thing that Professor May has said is that ugly facts trump a beautiful theory. But the really nice thing he said is that, of course, if the science is good, those ugly facts and the trumping of the bad, beautiful theory lead on to even more beautiful theories. A lovely start to the lecture series. Thank you very much indeed.